Welcome. So today we get a very exciting theorem. It's the fundamental theorem of calculus. It's named that way because, well, it's fundamental. No, actually, it relates to very big parts of calculus, derivatives and integrals together in one theorem. So we'll do the theorem and then we'll talk about examples. Now the theorem can be proved, and most books do prove it, but I kind of think we'll just use it rather than prove it today. So the theorem is, suppose you have a function that has an antiderivative. So f, little f, has an antiderivative, big F, on the interval ab. What does that mean? It means that big F's derivative is little f. So big F is the antiderivative of little f. Anyway, what does that mean? It means the integral from a to b, the definite integral, is big F at the top endpoint minus big F at the little endpoint, the low endpoint. Excuse me. This has a derivative built in. This is the antiderivative. It relates the integral to the derivative because now, in a real sense, the integral is the antiderivative. If you recall, we had a notation for antiderivatives before. There's a reason for this. This notation without the a's and b's was just a general antiderivative. Now with an a and a b, you plug it in and take the difference. Anyway, let's do examples. Here are two. Try them out. Okay. Hopefully you had time to try there with the pause button. Now, I want the integral from 1 to 3 of x squared dx. I need to take an antiderivative of x squared. If you recall from section 4.9, we have, well, 1/3 x cubed. Now, that's the antiderivative. We need a notation to talk about this. We can say, with the b in there, with the a in there, but it gets awkward. So the notation I do is just like this. This is the antiderivative. And these are the inputs. So what that means is we plug this one in. Subtract off, plug that one in. Notationally, it's very efficient. This is a square bracket, so it's something we've used before. You can sometimes use a line or bracket either way. So, but now we just evaluate this. 3 times 3 times 3 divided by 3 is 9. Minus 1/3 equals 8 2/3. Or 8.666 repeated. If you do this with the Riemann sum with enough rectangles, you'll get pretty close to this. But if you do it this way, you get exactly the right answer. How about this one? Well, this one, you have to find some function whose derivative is 1 over 1 plus x squared. And hopefully, you remember that's the arctangent. So that's the inverse tangent at 5 minus the inverse tangent at 0. Now that is hard to do in your head. So I'm going to go get a calculator and I'm going to evaluate it using the calculator because I don't want to do it in my head. I get 1.373. But this is the calculus, this is just plugging in. Hopefully these two made some sense. Let's try two more, and I'll give you some seconds to work on this. Okay, with the pause button, you had all the time in the world. And what about this one? Well, hopefully you remember that there's an antiderivative, even with negatives. It's the natural log of x. And then you can start plugging this in, and because of the absolute value there, the minus is not going to be a problem. Except, let's go back to the theorem. Suppose little f has an antiderivative on the interval. So, let's consider this entire interval from -1 to +1. Going over here, the antiderivative is, well, that's good. Going here, the antiderivative is, well, that's good. But there's a problem at 0. At 0, this function doesn't even exist. Nor does that, which is good because they agree. But you can't plug a 0 in here. This one is not an antiderivative over that whole interval. This function actually doesn't exist at 0. And when you integrate, you get a problem. This does not cancel out in a useful way. It does not do a nice thing. Because the antiderivative has a problem, at x equals 0, we can't evaluate this. Okay, hopefully that didn't throw you too much. Let's do this one. All we need is an antiderivative for this. We go, well, that's x times e. Well, maybe I just do x. The antiderivative of x is 1/2 x squared. And then e to the x is e to the x. Except hopefully you know that's not going to work. Why? Because if I took the derivative of this, what would I use? I would use the product rule. And then I get 2 terms instead of just 1. So this is not the antiderivative. What is the antiderivative? Well, in truth, the antiderivative is trickier. It's x minus 1 times e to the x. Why is that? Well, let's take the derivative of this. Take the derivative of that using the product rule. The derivative will be the derivative of the first thing, which is 1, e to the x, plus the derivative of the second thing, e to the x, times the first one. So I get e to the x plus x e to the x minus e to the x is in fact e to the x times e to the x. So it does work. Why? Because it's complicated. The product rule is complicated, so ending up with a product should clue you in that we're going to have a trick. This one is beyond us right now. What you really use is something called integration by parts. That's not for now. But now that we know that this is an antiderivative, either by guessing or because I just told you, plug these values in. Put 1 in. We get 1 minus 1 e to the 1 minus, plug 0 in. 0 minus 1 e to the 0. Now 1 minus 1 is 0, so 0 times anything is 0. 0 minus 1 is minus 1, that's 1. I just get a total of 1. This function's integral is 1. Hopefully, the first two made a lot of sense, and these two showed you that it's not exactly as easy as that. Until next time, this is Dr. J.